Hello, everyone. Again, welcome to our TransferLab seminar. This week, we have Timo Freiesleben. Timo received his PhD from the Maximilians University, where he worked on explainable AI and what explainable AI actually explains and fundamental questions around explainability. And he went on to his postdoc at the University of Tübingen, where he has been working on fairness and around healthcare and also explainable AI. He's interested in explainability for science, and so in applications of explainability in machine learning for science. And today's talk would be what you can read here about doing scientific inference using interpretable machine learning. So, Timo, the stage is yours.
Thanks for the nice intro. If you cannot hear me at some point or my mic is not that good because I'm on vacation at the moment, just let me know. Yeah, so the title is Scientific Inference with Interpretable Machine Learning, Analyzing Models to Learn about Real-World Phenomena. And it's joint work with Christoph Molnar and Álvaro Quintero. Álvaro was my second supervisor in my PhD, and I think you already heard a talk from him in the seminar. So this is the plan for the talk, the structure for the talk. I start with motivation, and then I will talk about traditional scientific inference, like how we used to do scientific inference with interpretable models. Then I will discuss my theory or our theory of property descriptors, and I will end with a discussion. So I think most of you are roughly familiar with what interpretable machine learning is about. Often it's also referred to as explainable AI. Some people differentiate between the two, but I will not. So I will mostly focus on model agnostic methods. So the case where you have some inputs X and your prediction Y hat, and in between there's your black box, your ML model. And what you're doing is you're changing X in a certain way. You manipulate your inputs and look at how this affects your model prediction. And by summarizing these data, like that you generate between X and Y hat, you then give a description of your model. And as you might know, there's like a lot of different methods. I would call it a method zoo. So there's a variety of methods, and every week, basically, there's a new method coming up. So there are some methods that are very popular, and these are the ones that I show here. So there are Shapley values. Shapley values show you, for the prediction, how important each individual feature was for this particular prediction. And it gives you some kind of fair contribution of each feature because it looks at all the different combinations of features. Then there's Lime. And in the case of Lime, what you do is you locally approximate your complex ML model. So you look at approximate your complex ML model by some kind of interpretable model, for example, a linear model. Then there's counterfactuals, counterfactual explanations. This is the technique I work most on in my research so far. And so the key idea is you look at an individual input, an individual instance, and then you look at how you can get, like this input X here, how you can cross the decision boundary closest way. And there could be different notions of closeness, and it's also something that I worked on recently, how you can guarantee plausibility of counterfactuals, so that you take this path rather than this path. And finally, there's a lot of different saliency maps that show you the most salient features in a prediction. And each of them, I think they roughly state they're doing the same thing, but they have very different outcomes, as you can see here. And some of them overlap, but many of them don't. And there's a big criticism of these kind of saliency maps because they have this disagreement problem. Because I'm, like, from my background, I'm a mix between a philosopher and a mathematician, so I like to ask very fundamental questions. And one very fundamental question that comes to mind if you think about this method zoo is the question of what these methods are actually doing. So what is the problem that is solved by these methods? And if you look into the research papers, you often see there's like a long list of motivations, what you could do. But for none of these, it's shown in the end that's actually doing this thing, that you can actually use this. And this is why at some point I was very annoyed and started writing a paper on this. This is a caricature that I draw for this paper. And the paper is entitled Dear XAI Community, We Need to Talk. So I used this here also to make some self-advertisement for my work. And yeah, so I think this is a big problem that we have in interpretable machine learning. Something that I'm very much interested in is interpretable machine learning for science. And this is why I recently started writing a book together with my friend Christoph Wollner on this topic. Also because this is what really started off this research project I'm presenting today, has started off this book, because we were discussing how can we use interpretable machine learning for science and how can we use ML in science more generally. And these fundamental questions led to this paper, and in the end also led to this book. And it's already available, so there's still some chapters missing, but we are on the way of publishing it. What I think is very important for understanding the current project is an important distinction between auditing a model and doing scientific inference. So I think almost all techniques in interpretable machine learning, they are concerned with model audit. So you have these input variables and you have your prediction and you change your inputs in certain ways and then look at how they change the prediction. So what you're interested in understanding is the ML model, so this process here. In scientific inference, you're interested in nature. So you're interested in how nature connects certain features. You're interested in the distributions in the world rather than how the model behaves. So you're interested in the relationship between X and Y. And as you might think, so the question is, how are these two connected? So can we analyze this object here and thereby learn something about this relationship? What we show in the paper is that we can do this. And also what we clarify is what kind of methods allow you to do this. So the example that I will use throughout the paper is the following. So imagine there's a social scientist who's interested in education. Let's call her Laura, and she studies the relationship between language and math skills. So this is the key question she's interested in, but she's also more generally interested in how can we predict math skills or Portuguese skills based on certain features. So the data that we used for this case, mostly for illustrative purposes, it's not to show how a particular method works, but rather to illustrate the general idea. And it contains certain features, for example, the student grades, the jobs of the parents, their education, then the age, tutoring, and absence of the students, and so on and so forth. Imagine you now trained a predictor that predicts the math grade from all these other features. One thing you might be interested in, or one thing that you might want to look at if you want to understand how math skills and Portuguese skills are connected, is to use the individual conditional expectation curves, so-called ICE curves. To understand this here in the Portuguese grading system, grades are between 0 and 20 is the best, and 0 is the worst. To understand what an ICE curve is, so very simple example. So imagine I'm part of this data set. So there's Timo. I don't speak any Portuguese, so my grade would be 0, would be very bad. I didn't take any tutoring, and at the same time, I have a lot of absences in the class because I didn't attend any of them. So you can imagine me being somewhere on this side, and what you're now analyzing is, to get an ICE curve, is you take this individual point and you predict the math grade for it. And now you do the same, but you change the Portuguese grade. So you change it from 0 to 1 to 2 and so on and so forth until 20. And what you get is an individual ICE curve here. Okay, if you now look at all these kinds of different data that you have in your data set, you get a lot of different ICE curves. And in order to obtain the partial dependence plot, what you do is you average over these different ICE curves. So this is the quantity that you see on the right-hand side here. And what Laura might be asking is, can she use this relationship that she mapped here using the PDP? Can she use this to make a scientific claim about the relationship between Portuguese and math grade? And we will show later that for this case it might not work, but in general, she can use interpretable machine learning to do such things. Okay, so this was the motivation. Next, I want to continue with like a comparison between inference with machine learning and inference with more traditional scientific models. How did we do scientific inference? How did we learn about the world by analyzing models? How did we do this traditionally? And the feature that we identified is what we called elementwise representation or elementwise representationality. So it's the case where each of the elements in your model represents an element in your phenomenon that you're studying. So there's a one-to-one correspondence between the variables you have in your model and the components that you have in the world, the relations that you have in your, like the functions that you have in the model, and the dependencies that you have, that you see, that you can observe in the world, and the parameters in your model and the properties of the real-world phenomenon. So there's this one-to-one mapping. And this is very appealing. I mean, if you, for example, from physics, this is what you usually have. Each of the objects, of the elements in your model are something you understand, that you can relate to your phenomenon. And this is very appealing because on the one hand side, it's cognitively appealing. So we like to think that way. So we like to have these kind of representations. At the same time, it's very nice for constructing models. So say you have a model for a particular phenomenon, and now you realize that there's something missing. And what these element-wise representational models really allow you to do is to extend the model very naturally. So you just add a new parameter, for example. You add a new feature. So this is very powerful, and as you might know, in machine learning, this is usually not really given. So if you want to extend your model with a new feature, you have to retrain the entire model, usually. What is very important is that it allows inference from the model to the world. So usually what you can do is you can analyze relationships between those three things and then draw inferences about the underlying reality. And the reason is that you have this kind of representation. A representation is always some kind of structure preservation between two different objects. A very simple example is, like, a lot of my colleagues are from statistics, so they like to think in linear models. And this is the most simple linear model that you can think of. There's just one predictor variable and a simple target variable. So let's say that y is math and xp is the Portuguese grade. And the underlying assumption that is often made in statistics is that the true dependency between math and Portuguese grade can be modeled by this kind of linear model, this kind of linear dependency, where you have the intercept term, you have the coefficient, and you have some kind of noise. So what you might do is you use the least square methods and then fit this model, and then you can always infer something also about your coefficients. So your coefficient is saying something like how strongly is this variable y, your target variable, related to your Portuguese grade. And what you can do, and it's very nice usually in statistics, is that you can get confidence intervals. So you get also uncertainties about how certain are you about this parameter being the true parameter. This is what we have in Bayesian inference. What you usually get in frequentist inference is how likely is the confidence interval you have, does it catch the true parameter? So it's a slightly different interpretation, but it's not really important here. And what I wanted to mention earlier is that ML models, they usually don't allow you this kind of inference because they don't allow you this kind of representation. So usually you drop all these very strong assumptions that you have in statistics, like linearity. So in a sense, you get scientifically more realist because usually this linearity assumption might be violated in the real world. However, you have to pay for that. And what you have to pay for it is that these model elements that you have, like the weights in your artificial network, for example, the activation functions you have, and all of that has no longer real meaning. So you cannot really easily interpret what they are responsible for, what they mean. And this leads to the problem that the classical way for doing scientific inference, so the standard approach, you just analyze these elements and then you learn something about the real world, is not really working anymore because you don't really understand what these elements are really doing. There are three ways that we identify in the paper to deal with that. And one thing would just be to say, well, we cannot do anything. So maybe these tools are really instrumentalist. We cannot learn anything scientific from analyzing them. And that is one position. The second one, you might know Chris Oler, I think he's still at Google. What he's really interested in is visualizing or understanding these individual units better. So maybe the problem is not that they don't represent something, but that we are really unclear on what they are representing. This might be another way. So what could you do? So what Chris Oler did in this 2020 article in DistilPub is that you look at individual elements in your model, for example, individual units, and you ask the question, what input combination would maximally trigger this particular unit? So would give the highest response in this unit. And what you obtain is these strange, nice, fancy kind of images. Not sure if you've seen them before. On the left-hand side, you might say, oh, well, nice. This might mean that the model is, what the model is looking on here, what kind of feature it's representing is the heads of cats, because this roughly looks like the head of a cat. Then you might look at another unit and say, oh, well, this might be looking at the front of cars, because this looks really like car-like. Well, it's at least what they say in the paper. And you might look at another unit and say, okay, this looks really like the feet of cat or whatever you can see here. So I think it's very difficult to interpret them. And I think that's a very general problem. The surprising thing, or maybe the unsurprising thing, is that all of these different pictures that I show you here, they're actually coming from triggering the same neuron. So it's actually the same unit that is triggered by all these different kinds of pictures that you see here. And this might already indicate, for me at least, this indicates that the assumption itself might be flawed. So I think the idea that artificial networks just learn the right concepts, exactly the concepts that humans learn, is actually flawed. And I think they don't have to learn these concepts in order to perform the same tasks. Because I think there's a variety of other concepts. Actually, I also have a paper on that. I didn't reference it here. But I think this assumption is just flawed. And it might be that in the future we can enforce models to do this. But at the moment, I think we don't have this property. So there's a final option, which was also proposed by Kishi and Kaiser in one of their papers, and is to say, let's use interpretable machine learning. Let's use these techniques that we discussed in the beginning in order to do scientific inference. But they stay very vague on how we could do this. So the idea with this paper was, let's make this very clear on how to do scientific inference with interpretable machine learning. The problem that we see is that in the current literature, we are mainly focusing on this question here. And to do scientific inference, you should be interested in this question here. And you need to be interested in the relationship between those two. We should be clear. So auditing a model is also a very important goal independent of doing scientific inference. So we need both of them. We need to understand both of these paths. It's still a different task. So if you want to do scientific inference, you should trust in your model. So you need to have like a well-trained model. You need a model that you know like behaves in the right ways. You need to do a lot of model auditing until in the end you can perform scientific inference. So in a sense, they're very interactive, complementary goals, but at the same time, they're distinct goals. So this leads me to the core part of the paper, the most meat is. If you remember the picture that I gave you earlier about elementwise representation, the idea of holistic representation is maybe we don't know like what the individual elements are doing in your model. Maybe we don't know what the weights are representing. We don't know like what the activation functions are representing, but maybe we know what the overall function is representing. Maybe we know what the overall function is roughly approximating. If we know that, maybe we can match the properties of our phenomenon with this kind of descriptors, with these kind of descriptions of our whole process. If you remember from the beginning, this is what IML techniques are ultimately doing. So they're analyzing the whole thing and then giving some kind of summary statistics, some kind of aspects of this complex object. And the same idea is underlying here. So if we understand what the whole thing is doing, then we can give a meaning to what these IML descriptions are doing. This directly triggers you to ask, like, what are ML models representing? And this is a difficult question. However, we are very lucky with the paper because people already solved this in statistical learning theory, because we know what models are ultimately approximating. They're approximating the base optimal predictor. And the base optimal predictor gives you, in theory, what would be the best possible predictor that you can build, given you have a certain kind of data. And this clearly depends on what kind of loss function you apply. So, for example, if you have the mean squared error, if you have this loss function here, then the base optimal predictor would be the condition of expectation of y given x. So this mathematical object. This, at least in theory, gives you an idea about what this whole model is representing. It represents these complex aspects of your joint probability distribution. Another one, let's say we have the 0-1 loss. In this case, what you would get is the most likely class given these input features. And for cross entropy, like if you have this more complex kind of loss, and you're predicting probabilities, what you're approximating is the true conditional probability distribution of y given x. So what these IML techniques are ultimately doing is they take these very complex objects and they look at very specific aspects of these objects. You can imagine IML techniques for science like some kind of magnifier. So you have complex objects, and then you take this magnifier and you look at one specific aspect of them. The key question for our paper was, how can we describe the process for building such magnifiers, and for building the right magnifiers? So we identified 4 steps. I think in an earlier version it was 5 steps, but in a peer review process, so the paper is almost true. Finally, we reduced it to 4 steps because it was more beautiful, I think. So the first step is you have to formalize your scientific question as a statistical estimate. This is a very crucial step. You want to connect a scientific question to the solution that you ultimately get. As I said earlier, I think this is very often missing in current IML. As a second step, you have to identify the estimate. So you have to, I will show you in like a second more detail what I mean by each of these steps. But what you have to do is you identify your estimate. You try to use a property descriptor. You use some kind of description model in order to get your estimate, given you had the perfect predictor. The perfect predictor is here denoted by M. As a next step, in reality, usually you have finite data. So what you do is you estimate your property descriptions. And finally, you have to quantify uncertainties. The different things that you see above and above here, explain them in more detail in a second. Let's start with step number 1. You have to formalize your scientific question. So in the case of Laura from the beginning, you might ask the question, how are language skills associated with math skills? And one way, and maybe not the smartest way of describing this question formally, is to pose it as asking for the conditional expectation of y given xp. So the conditional expectation of the math grade given the polygons grade that you see here. This might be one way of phrasing a scientific question in forms of formal language, in forms of the distribution of features. So the second step is the most crucial one. So it asks the question, if I had the perfect predictor, are there transformations that allow me to get to my Q, to my question, that allow me to identify my question? And usually you need something more. Usually the perfect predictor is not enough. So even if you had the perfect predictor available, it wouldn't be possible, because you also need to know something about how your inputs are distributed, how your input features are distributed. This is what we call the probabilistic knowledge K. If you think back to the example, like this was your target estimate Q, is there a way to transform your perfect predictor M to get there? And as we show here in this equation, there actually is. So if you take Mx, if you take your perfect predictor, and you look at the conditional expectation given xp, then what you obtain is Q. There's some math going on. This is the so-called Tower rule. And with this, you can actually identify Q. So if you had perfect conditions, you could answer your question perfectly. The function that allows you to answer the question, so the function, the transformation that leads M into Q, is what we call the property descriptor. And this is what later will be the interpretability method. So this is just a very general definition of an interpretability method that allows you to identify your question. We propose that it's a continuous function, gk, that identifies Q given k. The reason why we want it to be continuous, you don't have to post this requirement, you can. The reason why we would like to have it continuous is because if it's not continuous and you have slight variations, then you know that your model is not perfect. You probably know that the probabilistic knowledge you have, the k, is also not perfect. So your answer will be far off if it's not even continuous. So this is why we post this additional assumption. The object that we have here, like this conditional expectation x minus p given xp, if you substitute this M now with your machine learning model, then what you get is the conditional partial dependence plot. This is the definition of the conditional partial dependence plot. So it's a version of the partial dependence plot like the one that you've seen before, but it takes into account the dependencies. So it would not summarize about over all the ice curves, but only about aspects of the ice curves where the feature combinations are realistic. So in theory, everything is nice. In theory, you have the perfect predictor. In theory, you have perfect probabilistic knowledge K. In practice, what you have is data. And what you need is like a way to approximate these terms by using data and by using your ML model instead of the perfect model. What you do is you define like an unbiased estimator of GK. And this is generally possible. And ultimately, Laura gets her question answered. So this is the answer that Laura gets. She just has this unbiased estimator of GK. She plugs in her data and gets this kind of curve. So the question is now, can she just use this curve immediately and analyze it and use it for a scientific inference? Can she now say, well, Portuguese grade and math grade seem to be strongly correlated, especially in this middle area, but not so much between the grade 16 and 20 and say 0 to 6. In between is roughly a linear relationship. Is this like an inference that she is allowed to draw? Well, not really, because there's some problems. If you look at the data distribution, so there's a lot of students with Portuguese grades above 7 and below like 18, but not so many that have higher grades and not so many that have lower grades. So your model is not really that trustworthy for these kind of cases. So there's a lot of uncertainty that is contained here. This kind of uncertainty is something that we show how to define for these cases. And the thing is, we make two different kinds of errors. So the first kind of error happens because we do not have the optimal model. We only have our trained ML model that's suboptimal. I mean, hopefully it will be really good, but it will not be perfect. So this is what we call a model error. And secondly, we only have finite data. So this is what we call the estimation error. Because in order to get your estimates, you often have these kind of Monte Carlo methods, for example. They give you some kind of estimation error because they're really dependent on the data that you plugged in a specific case. And if you vary that, you obtain a very different prediction. And as you can see here, so this estimation error is mainly highlighted on the left-hand side. It's rather big if you go to these areas where we have very little data, but not so high if you climb up more here, like in between 6 and 20. So there our estimates are roughly good if you think only of the estimation error. If you take into account both the estimation error and the model error, what you see is your error gets very big in the beginning. And this is because like your model can have very different kinds of behavior and still fit your data in a very strongly fit your data. So the uncertainty here is just very high. And these are the 95% confidence intervals that you can see here. Again, on the right-hand side, you see the same behavior. So if you look at the rates above 16 or I think it's again 18, then your confidence intervals turn very wide. And in the paper, we show how these kind of uncertainties can be quantified for every possible property descriptor. And actually, we have another paper together with Christoph. Christoph is the first author where we show the math behind this in more detail. So this was more of a philosophical paper where we showed a general way, the general idea of how to define these property descriptors. In the other paper, we show specifically how to do this for the partial dependence plot and for the feature importance. What's nice is that many IML techniques that are on the market, they can already allow you for scientific inference. So in a sense, you could say they already act as property descriptors. They already have the nice theoretical foundation that we demand for property descriptors. And one of them is the conditional feature importance. Similarly, if you look at a local question, this is the ICE curve, like it's not ICE curve, but the individual conditional importance. Actually, a friend of mine has written this paper, like Giuseppe Casalicchio, also from the IML group in Munich. Then there is these Shapley-based techniques. So the global Shapley-based technique is the stage. The local Shapley-based technique is that allows you for scientific inference is the conditional Shapley value. It's slightly different than the classical Shapley value because you be conditional, so you try to stick to your data manifold. And the kind of question that you might be interested in is which student information should educators track? And you might argue that the information that educators should track is the ones that contain the biggest importance, so that carry a lot of importance, like carry a lot of information about your target variable. And so you can use all these different kinds of techniques for very similar kind of questions. I mean, there's a slight difference between those two. So you can see these, for example, you can see SAGE as like looking at different conditional feature importances and averaging over them. And you can make a similar argument here for the relationship between ICI and the conditional Shapley values. So it's slightly different, but it's in both cases, what you're really interested in is how important is a feature in order to predict the target, and so how much information is contained in the feature. Similarly, you can ask questions for feature effects and for relevant values. So for example, if you ask for feature effects, that's what we did the whole time in the example. This is where we discussed these ice curves and conditional partial dependence plots. So like Laura asking, how does the language skill influence the math skill? Or how influences parents' education the students' math skills? So all these kind of questions can be answered using these kind of techniques. I think there are also others, but yeah, these are the very prominent ones in the literature. There's ALE plots as well, which are very similar and a bit more general than the conditional partial dependence plot. I mainly used it for illustrative purposes. And finally, there's relevant values. So you can ask the question, what characterizes more or less successful students? And if you ask this question for a particular student, so how would this student be more successful? This is a counterfactual. If you ask more globally, what characterizes a successful student, then there's a method called PRIM. It's actually a paper from 1999, and I didn't know about it, but the reviewer knew it, and it was very nice because we had a very good reviewer who knew the literature very well, so it was very nice to be pointed to this paper. As usual, like in interpretable machine learning, very often you find out that people in the past already did things that you're doing at the moment, they just used a different name. This is again a caricature from my opinion paper from the beginning. What you might say now is like, isn't there this disagreement problem? So you have all these different kinds of feature importance, and they give you different feature importances for a very same model. So how can that be? Doesn't this mean that they're actually like not reasonably defined, and actually they don't allow you for scientific inference? Because if they give you just different importances, the scientist might just use the object that she likes best. She might just interpret the data in the way she likes best, and this is not very objective. And actually there's a paper, I forgot the author actually, I think it's from Krishna, and they show that people are actually doing this. So at the moment, this is the problem. So people are just using the technique that gives them the insight they want to have. For like scientific honesty, this is very problematic. However, if you have our framework of property descriptors, if you understand what you're estimating, if you understand your estimate, then this cannot happen. Because if two ML techniques disagree, even for enough data, then this just means they have different estimates. And different estimates just means you're interested in different aspects of your data. And if they're interested in different aspects of their data, they're allowed to disagree. That's something that we also argue in the paper. When I talked about this paper with others, like both in philosophy and in science, they very often, like they had this question from the beginning to the end. So what about causality? If you talk about scientific inference, people are ultimately interested in causal questions and not so much in whatever we describe. Like, for example, Laura, she might not be interested in how are they associated, but is one causing the other? So an interventional question in the language of causal modeling would be, would tutoring in Portuguese improve students' math skills? So, I mean, this is much more insightful, because if we knew that tutoring in Portuguese would improve student math skills, then this could be the foundation of a policy intervention. We might argue, well, we need to give students better teaching in Portuguese in order to improve their math skills. Then there's more complex, like even more complex questions that you could ask, like counterfactual questions. So you have a specific student that failed. You could ask, did the student fail in math because of her Portuguese skill? So was her Portuguese skill just not good enough in order to understand the math because the math was presented in Portuguese? So I think these questions are much more fundamental, and I totally understand why everyone is more interested in these kind of questions. However, and that's one part of our contribution of the paper, is to make very clear, without further assumptions, ML techniques and property descriptors, and specifically, they describe only associational quantities. They don't give you causal insight in general. Even though you intervene on inputs, that doesn't mean you necessarily can interpret them causally concerning your phenomenon. If you want to pose causal questions, that's something you can do. And that's something you can also do with interpretable machine learning. However, what you need is you need much stronger assumptions. You need assumptions, like you need an extra layer in your pipeline. You could think of this as a step 0 that establishes whether your causal question, your causal quantity, can be translated into an associational quantity. There's this really cool framework of targeted learning that does exactly that. What they do is they have this 0th step where they ask the question, what is your causal question? Can it be translated into an associational question? And how can it be estimated? And in a sense, it often works much better than using interpretable machine learning. And so this is a clear limitation of interpretable machine learning in general for science, because in a sense, you're doing a detour. So what you're doing, if you think of the conditional partial dependence plot, so you started by training this huge model, with this very, very big complex model, and now you're reducing complexity to a very simple aspect of it. And what you could do instead is you could just directly estimate this aspect. And this is what targeted learning is for, what it is designed for. And I think it often makes much more sense than using interpretable machine learning that just directly use targeted learning and you directly estimate the aspect that you're interested in. Second limitation, and it's again a very big one, I always talk about you need conditional versions. You need IML techniques that try to stick to the data manifold. However, for this, you need conditional sampling. And conditional sampling is something like you have to train an additional model. And this is a very difficult problem. It's at least as hard as the prediction problem you had in the beginning. And there's work on how to do this and how to do it efficiently, but it's just adding another source of uncertainty and another dimension of problems to your modeling. And you should be aware of that. And I guess many people in this audience are concerned with deep learning, and they work with images and with sound data. And asking them to formulate a question in terms of the joint distribution of X and Y is very difficult. And it's not like I have an easy solution for that. It's not like I can show you how to easily formalize questions in terms of pixels that are actually concerning the objects in the image. And I think this is a very general problem in interpretable machine learning. I think we need to understand, we need to find out how the relationship is between pixels and objects. And there's work like concept bottleneck models that go in this direction. And I think causal representation learning, which is very popular in Tübingen, for example, is another way of going for this. I think that's definitely needed in order to bring scientific inference also to image domains and sound for sound data. So to conclude, so the problem that we identified is that scientific inference via model elements is not available in machine learning because these elements don't represent. And current IML is not solving the problem because it often mixes different desiderata. However, our solution is that if you interrogate your model in the right way, if you ask the right questions to your model, then you can actually learn something about the process that underlies your data. Okay, I'm happy to get your questions. Thank you for your attention.